Hello and welcome to my presentation on how to over-engineer things and have fun. It's going to be an odyssey into building a modern, distributed, real-time Wi-Fi spying system. My name is Otto Bergles. I'm software engineer and software architect and consultant. I currently work for a company called Global Web Index. And my job on day-to-day is basically to explore technology, the landscape, and to help clients build new innovative scalable products. So basically, my job day to day is to explore new stuff, build prototypes, and have fun while building it. And today, I'm going to show you how you can build an interesting product on top of Kafka, and how Kafka can also be a fun experience, and how you can build something incredible on top of it. So first, let's talk a bit more about what over-engineering actually is. Over-engineering is an act of designing a product to be more robust or have more features than it's necessary for intended use. It's to build something that might be what's also known as an overkill. So build something that will do something that perhaps it shouldn't do in the first place. And our story begins, like many stories, by a bunch of guys talking together over a cup of coffee. And one of my friends is a security expert. Now, the security expert could be also a code name for a hacker. So a hacker that has turned his passion and love for building and breaking stuff into a profession, and now wants to help companies secure their networks, secure their apps, and make sure that companies and private citizens don't lose their valuable data. And on this nice coffee break, he told me about this very interesting gap or a flaw in the Wi-Fi, in the wireless networks. Specifically, he told me that there is a way to listen to devices trying to connect to existing or non-existing access points, and that kind of information could be used so for some malicious actors willingly, unwillingly to do different kind of things. And that kind of discussion led into building and researching this space more. And essentially, it gave me a really good playground to play around with Kafka and few technologies on top of it. And that's how the project was actually born. Now, before I can tell you a bit more about the project and the solution itself, we need to go back and we need to talk a bit more about Wi-Fi and its basics, how you can use, how this thing actually works on a higher level. So Wi-Fi in most common form in your home, in your office, works with two main components. You have access points and you have devices, or in formal terminology, also known as stations. And these access points, or you may know them as routers or wireless routers, enable devices connections. And this nice sketch on the left side of your screen, you see two wireless access points, and they have a lot of different devices that connect to them. You'll probably think about your computer being connected to wireless. You also think about your smartphone. But as the civilization evolves, more and more devices, the smarter devices, get connected to these networks. So there is a lot of traffic going around the radio space that Wi-Fi uses. Now, the challenge or the way you can also these things connect together is described on the right side of your screen. So you have what's described here on the right side of your screen, a sketch of how the handshake or the exchange between the station and access point actually happen. So when you turn on your device, your phone, for example, and when you activate the wireless on that device will send probe request, and it will try to connect to known or unknown wireless access points. And these access points will get that request and they will reply back. And if the device and the access point know each other, they will try to establish the connection. Now, the problematic part, or the tricky part, or interesting part, and this is that these probes can be scooped out of the thin air, essentially. And if you put some kind of device like a Raspberry Pi sketch here on the left side in the middle of this exchange, you can start listening to what devices are trying to connect to and what access points these devices are actually already connected to. So the idea is to build something, put it in the middle of this wild wireless space and try to capture as much data as possible. Or to frame the whole idea a bit better, the basic challenge here is to capture all the data that's floating around, then visualize the result. And in essence, a pretty simple idea. And that idea needed a name. It needed to be contextualized in some broader spectrum. And in security research field, there is a so-called Oracle attack, which is an attack that exploits a vulnerability or weakness in a system that can be used as an oracle to give indication or to tell the attacker that he or she has reached or is nearing its goal. So the idea is to build a passive instrument that will sniff or monitor or collect all these various requests, and then it will try to help us understand what's going around. That's why this code name has emerged, and all the code that you'll see is also packaged under this name, and it's completely open source, so you can look at it yourself. Now, the basic path that you would take when you try to build such system is the following. You start first by building a prototype device, you then capture the data, you then process the data, and the fourth step is usually you try to visualize results through charts or something, right? But the problem with such approach is that it's usually not that exciting, or it's not that fun, and very likely a lot of you guys have probably seen the similar approaches or have already explored similar spaces. But wouldn't it be nice if we would spice that kind of challenge with additional requirements? So this is the part where the whole over-engineering comes into place. So we decided that instead of building just one device, we're going to build several devices. Instead of capturing just some data points, we're going to capture all the data points that you can get from such system. And we're going to do that in real time. And to make things more exciting from processing perspective, we're going to process the data anywhere, in meaning that if we decide that this is going to be represented as a graph, we can do it in graph database. If we want to represent this in a chart in some analytical tools, we can do that. So the post-processing should essentially be decoupled from the collection and pipelining. And the visualization results should also be as snappy and as real-time as possible. And to really up the game, we decided that we should not lose any of the data that's being collected. So instead of, if a device is down, or if the network is down, or if the device restarts or whatever, none of the data should actually be lost. And we want to use, the most modern technologies that exist out there in order to make our lives easy. And, we don't want to build very complicated pipelining. We want to use technologies that come pre-prepared and already exist for such tools. So we want to use modern tools, and we want to have fun building this exciting part of the thing and not waste time on old and cumbersome processes that were done before already. So with that in mind, we come to the first part of this journey, building the actual devices. So the first prototype was actually this little device that's pictured here on the bottom of your screen. This device is called Wi-Fi Pineapple Nano. It comes from a collective or organization called Hack5. And Wi-Fi Pineapple is penetration testers platform that helps you do reconnaissance work, credential harvesting, open source intelligence gathering, and it helps you do any kind of sophisticated and not so sophisticated Wi-Fi work. It's essentially a little dongle that you put into your laptop or a machine, and you operate through either via SSH session, or it has also a very nice clean UI. And this little thing also has two antennas, as you can see, and it's also has a suite of tools that you can use for doing this kind of Wi-Fi hacking and cracking tool. It comes with software or a suite of tools that are common to Wi-Fi researchers. They're known as AirCrack, and the AirCrack package also has a tool called AirDump. So what you now see on your screen is a session from a tool called AirDump that's running on this little device here. And this tool puts one of the wireless cards into the so-called monitoring mode, which means that the wireless card will intercept all the Wi-Fi traffic, and it will try to picture that information through this user interface. The user interface, it's divided into two segments. On the bottom of the screen, you see the stations, the devices, and you see that these devices are probing for specific wireless access points. On top of the screen, you see the access points that were already found, and you also see, for example, the encryption these access points use, authentication systems, power beacons, etc. So this is essentially what you can use and what you can get essentially on any kind of modern Linux machine or wherever you want to run Wi-Fi reconnaissance work. And the only requirements from hardware perspective is that the device needs to have wireless access, wireless card that can be put into this wireless monitoring mode. And you can see that with these tools and this kind of hardware, you can quite quickly get to a stage where you can do this kind of exploratory work. However, the first prototype was not that fun to use. It has some advantages, so it was quite easy to set it up. It was easy to experiment. It has some really good documentation. It didn't consume a lot of power, and it comes with tools that you can already use as a security researcher or penetration tester. But it has minuses for development of such products. So it's embedded device. It has MIPS architecture. It doesn't have a lot of space, so you cannot actually deploy a lot of different software to it. And it also has a very limited antenna. And because it's not that popular for such use cases, a lot of the tooling is also a bit outdated, which doesn't make it a really nice platform for doing any kind of exploratory or research work. So that leads us to more experiments and more prototypes. So here we have a second iteration of the device. So it's still a Wi-Fi Pineapple, but now it has in the middle another Raspberry Pi, and on the bottom it has USB Power Hub. So the idea here was that instead of doing the processing and running the software actually on the Wi-Fi Pineapple, that was moved to Raspberry Pi, and the Wi-Fi Pineapple was merely used as essentially as an antenna. And that was then the second iteration of this product. Now, to make things more exciting, more fun, we started exploring ways and building more of these little devices. And you can see that here I started using different antennas. Here you have another very popular antenna in this security research field from a company called Alpha Networks, and it's essentially a card that you can see in the device in the middle has replaced the pineapple, and from there on I started using a lot of different antennas and devices, etc. Although you could use a lot of very sophisticated antennas, or you can use very interesting and powerful combination of antennas. You could also use very old Wi-Fi cards that just need to have the wireless monitoring mode. And you can see here on the right side there is a very old Netgear dongle put into network monitoring mode, and it's also a very valid solution. Now, to have more fun, it's also a good idea to go bigger. So here you have another Alpha Networks wireless card. In this case, you can see that it has 4 antennas, which means that you can scan more channels concurrently, which means that you can capture more data with better frequency and with better accuracy. And to make things more interesting and more challenging, we also started experimenting with these little things in the middle. These are so-called GPS dongles. They are essentially GPS chips that you can put into your machine, and the software can then receive GPS signal, which means that these devices, in some cases, have now also started receiving GPS coordinates, which means that you can, for example, put one of these devices in your car and you can walk and you can drive around and you can start collecting wireless data with location as well, which is another interesting challenge. Now, in order to have even more fun, it's also interesting to include more people. And given the situation in which world is currently, I've used the lockdown to also include my kids in this experimentation. So here you can see my daughter and my son trying to build and trying to help me build these devices. And I was trying to teach them that building these things is not as hard as you usually perceived. And on the right side of your screen, you can also see now another device which is running not on Raspberry Pi but on very powerful desktop Intel NUC, which is a very powerful machine. So essentially a replacement for a laptop, and again another device on top. So in conclusion, from hardware perspective, we built 5 different custom-made devices. They have very different operating systems. They have very different hardware architectures, and they were distributed in different physical locations, and they have very different operating systems. So the purpose here was to explore how hard it is to essentially build on different platforms and how you can still rapidly develop things on these platforms. And that leads us to the next challenge. And the second challenge in this roadmap is then to capture all the data. And that leads us to the area of software that actually runs on these devices. So the software built here follows 3 core concepts or 3 core principles. First is that it's all built around event streaming. Meaning the devices will emit events that actually happen in the real world. And the second big concept is resiliency, meaning that if the power goes down, if the network is broken, if the broker is unavailable or something like that, the system will react to it and it will adapt. So that once the situation is normalized, the system will emit the data that it has collected so far, and none of the data will be lost. And the third really important part of building such system is rapid development cycles. I wanted to be able to deploy new versions of the software rapidly, and it needs to be easy to debug and add new devices to the whole system. So this leads us to the next topic here. Why event streaming and how is event streaming related here? Event streaming is essentially trying to capture events that happen in the real world and try to model the system around it in a way that representation or state can be always rebuilt from the events that have happened in the real time in the past, which means that the events fly through the system and they're immutable, they are unchangeable through the whole development cycle and through the whole collection cycle. And we try not to lose any of these events, as they would also mean we would lose significant information. And when we do have a need to build a state or count things or represent this in some form, we will be able to build that state out of the data that was collected through the events. Now, this kind of concept is really neatly tied into the way this system actually works. So when we detect some kind of probe, when we detect new access point, we detect new device, that is always an event. Now, in practical terms, you can see a few examples of these events in this screen. So what you see on your screen is essentially a real-time feed that is slowed down, but you can see that these are events that are essentially JSON messages or JSON payloads, and that are sent from very different clients on different locations. And these events are tagged and they originate by the source, so from the devices themselves. And they represent actual events that have happened. The advantages of event streaming in the context of IoT, or in this case, is that events are easy to reason about. They represent something that has actually happened in some time in the real world. They're easy to distribute. They're easy to partition, to scale, to backup, etc. And it's easy to rebuild the state out of it. And even if something has changed historically, even the change is just another event, and that means that it's quite easy to build on top of these events. Now, another big advantage to such systems, if built properly, is that it's quite easy to build pipelines around it. So here you have two pictures. On the left, you have a picture of how most of the modern systems look if they haven't transitioned into more event-driven or event-based architectures. You have a lot of different components, databases, services, logging systems, aggregation frameworks, etc. And they're all connected via very different pipelining, in some cases via real-time feeds, in some cases via batch processing, etc., etc. And you can see that the things are very messy, and it's also very expensive to keep all these things connected and in sync. And just thinking about how much work would you put into building these blocks and ensuring that the collection is correct and that you haven't missed or dropped any kind of information when you build these arrows in your charts, as well as in your architectures. Now, in contrary, on the right side, you have a modern architecture where you put a Kafka in the heart of your business, essentially. And when you build your system on top of event streaming. So on the first layer, you see you have different apps, or systems or consumers or clients or whatever, and they interact with your existing databases or APIs. And all these interactions then generate directly events, or you generate some mutations that can again be represented via events. And these all are then emitted through Kafka streaming platform and to various topics. And then based on your use case, you can always transform these events, reprocess them, or you can channel them to some other components, etc. Now I'll try to demonstrate these concepts more in the following examples. But first, we'll talk a bit more about the Oracle Peak agent. So this is the software that's actually running on the device itself. It's a software that's written in Scala. It's written with Akka streams. It's Dockerized, meaning that it's quite easy to ship around. And although I also experimented with GraalVM, it's built still on top of OpenJDK, and it's deployed through Ansible to also explore a few other things. But essentially, schematics of the agent is as following. It's running on top of Docker daemon, and it's connected to two additional daemons. One is called BetterCap, which is essentially a tool similar to AirDump, and it connects to your wireless card, and it actually generates the stream of Wi-Fi related events, and these events are then post-processed in the agent and emitted to Mqtt. And very similarly, we also have another daemon called GPSD. If the device has GPS device connected, the GPSD will collect the GPS information and also send it through Oracle Peak agent to Mqtt. Now, when you boot up this client on the device, it looks something like this. It's not really exciting and fun screen to see, but you can see that it's booting up on different operating system. It's connected to Mqtt broker, and it's also connecting, receiving GPSD information, and that information is then broadcasted to the Mqtt broker. Now, at this point, I should probably tell you more about what Mqtt is and why it's used here. So Mqtt is a standard messaging protocol for Internet of Things. Its design is extremely lightweight PubSub or publish subscribe messaging transport, and it's ideal for connecting remote devices with small code footprint and minimal network bandwidth. It's today used for variety of very different industries, such as manufacturing, telecommunications, oil, gas, automotive, etc., etc. And the advantage of Mqtt is that it's a very scalable, very secure, reliable, message-driven protocol. It's also bidirectional, which means that although on this example on your screen, these devices are emitting the events, they can also equally subscribe and listen to events that could be sent to them. So you can operate through a device through Mqtt. And in essence, this Mqtt protocol is very simple and easy to implement, which makes it a very good candidate for IoT devices that should consume small amounts of energy and that they work in environments with unpredictable networks and unreliable networks, etc. So if we focus a bit more on what's happening on your screen, so here in the tree structure in this tool, you can see on the first level, you see essentially an environment with two different locations, and under these two locations, you'll see location 1 and location gigatrons. These two locations have, for example, in this case, two devices, and on these devices then emit information on specific topics like this. So you can see here information about access points and events as they are generated on this thing. Mqtt itself was built in the 90s as a replacement for traditional SCADA systems and to replace telemetric systems that were used at the time, and to try to build a new and open standard for building this kind of tools and control systems. Initially, this Mqtt was designed to operate tools via satellite. So the protocol itself was built to have a very small footprint, and it's reliable and you can use it quite easily on various different platforms. With that said, this is a screenshot of the code that's actually deployed to these devices. You can see here that that although the code is a bit long, it's more or less all the code that's actually deployed to these devices. It's built on top of Akka Streams, and because Akka Streams is quite sophisticated and has a lot of very different concepts that could be used here, we get a lot of very powerful concepts. So, for example, one of the concepts used here is concept of backing off. So, for example, if the software could not reach the broker, or if the daemon would be down, or if something would be wrong, the system has backup strategy, and it will try to delay retries before it will try to send the message again, which means that these things will be more robust and resilient to unreliable networks. And like I said, majority of the code is on your screen, so it's quite clean and quite easy to write and quite easy to maintain. And it's also easy to ship around with existing tool sets. So that brings us to processing the data anywhere, and that's essentially where you will find more of Kafka. So the flow is this: we take the data from Mqtt, we put it in Kafka, and then we ship the data, transform it, and store it into InfluxDB. And on top of it, we visualize that data in Grafana. And the data is then also sent and consumed via Neo4j, which is a graph database. And you can do some more exploratory graph-oriented visualization there. To be a bit more precise, we use here Kafka Connect. So what you see here in pink is our two main components of Kafka Connect. So we have Mqtt source, which is essentially connects to Mqtt broker and emits the information to three different topics. We then have two sinks, one for Neo4j and one for InfluxDB. And because you need to transform these events and merge topics and events together, you need additional component in your streaming system, and that's why ksqlDB is also used in this system. ksqlDB does additional enhancement of these events. Kafka Connect, as you know, it is a part of the Kafka platform, if you want, and it comes with a set of tools and a system that gives you a power to define these transformations, sinks and sources, where you connect to different components of your system, and then essentially ship the data in or out of Kafka. Here you have an example of Mqtt source. So this is the configuration that's used to connect Mqtt and Kafka together. You give it a topic from which it should read, and topic in Kafka to what the data should be, to where the data should be written to. You also equally define the sync connector like this. So we have a sync connector that will read data from Kafka topic and do some kind of transformation on top of that data with transformers, and it will write that data into Neo4j. An interesting note here on this sync configuration is that you can say to connector that it should read the data from the beginning of topic or from the end of the topic, or you could give it specific offset, which means that you can start integrating it various places. Here we have a few examples of the queries that were used to transform the events to data in the Neo4j. And ksqlDB, if you don't know it, is an event streaming database. It's very useful to do this kind of practical transformations on top of your event streaming sources. Here is an example that we used to transform very plainly information from Kafka topic in Avro format, transform it, enhance it in some way, and then store it in a JSON format. And the most interesting part of ksqlDB usage in this project is this case where you have access point information that's joined together with the location information that comes from different Kafka topics, which means that you can combine together very different data sources with the help of ksqlDB. Now, the fourth part is visualization of the results, the actual representation of this thing. So the first result is this thing. It shows the access point feed here. So all the access points that the system has detected with the meta information, the MAC addresses, etc. It also offers a current view, so the actual representation of what the system sees at a particular location. And on the third tab in the screen, you will also see the actual event stream from the system as events come through from different locations. This picture here is a snapshot from Grafana, and what you see on your screen is essentially representation of availability of particular devices through time. So where you see pink, the device was present in time. Where you see gray is where the device was not present. And if you visualize this thing even further, you can see this chart. So you can see the little pink transparent background represents the working hours. So when people are at work or when people are near these devices, you can see that the amount of devices detected significantly spikes. When people, go away from these locations, etc., the traffic significantly falls. And you can also see this little thing. This is essentially a Neo4j visualization of all this data. Neo4j is a graph database, and which means that you can represent the data through graphs. So what you see on your screen are two blue circles. These are essentially two access points, and the red circles represent location, and the orange circles represent actual devices that were detected. And as you'll see now, I'll try to visualize all the information around specific location. And what you see here is all the access points that were detected at specific location. So you can see that the same data that was collected was represented in one way through very linear charts, through session charts, and another visualization through a graph chart. So a few conclusions. Event streaming, as demonstrated, is extremely powerful, and it could be very useful for building IoT systems. It's interesting and fun experience to build these kind of things. You should definitely consider Kafka to be a backbone of your modern system. It has few very powerful concepts that will make your life very much easier. And Kafka connectors, Kafka, ksqlDB, and few components in the ecosystem will really help you build things without much code. I've also came to a conclusion that Scala could also be used for IoT agents, but it has some interesting quirks to it. And the another bullet point is that Wi-Fi as such has a few disadvantages because of the way how it was implemented, and that perhaps we should be more careful to what Wi-Fi devices, to what kind of Wi-Fi access points or Wi-Fi networks do we actually connect. And another key take is that you should explore, you should build these devices, and you'll learn a lot. And it's worth exploring on real use cases, and it's worth giving yourself a good challenge. You can learn a lot. And that concludes most of my presentation. At this point, I would like to thank all my friends, Andras, Josko, and of course my family and friends at Geekatrons that helped with this experiment. And if you want to learn more about the particular project, it's completely open source and available on the following link. Now, if you have more questions, this is also my contacts. I'll be happy to answer any of the questions that you might have. And I hope that you've learned something today and that you'll find these challenges exciting, and that you will explore these technologies yourself as well. So that concludes my talk.